now that we know how to find all of the roots of any complex number, so we can be given any complex number, z, no matter what it is, so a pure real number, a pure imaginary number, any number in the complex plane, okay, and then we could be asked to list all of the nth roots of this number. For example, maybe list all of the fifth roots of the complex number. Well, we know the general rule is that any complex number is going to have exactly nth roots. So that means that there's going to be exactly 5 complex numbers that when you raise them to the 5th power, you're going to get z. There's exactly 5 fifth roots of z. That's the rule. Okay, and we know how to find all 5 of those. For any complex number, we can find all nth roots of that number, no problem. Okay, so but with that, there naturally comes in some confusion regarding the radical symbol. Okay, so yeah, I mean we've got this radical symbol that we work with, right? And we know that the radical symbol in general, it's got an index n, an argument a, called the radicand. Okay, and this means it's the principal nth root of this number. So remember, it's not, you don't just use the term principal for like an even root or a square root. No, the radical symbol means principal root. Like this is the principal nth root of this number. Okay, and just to review exactly how we interpret this across the board. So this is equal to, the principal nth root of a is equal to a single number b, which means that b to the n power is equal to a. Okay, now, but in the context of when we learned this in pre-algebra, we had no awareness of an imaginary number. So what was implied was that a could be any real number and b could be any real number. And the only restriction was that n was some positive integer that was greater than 1. Right? So n, we don't have an index of 1 or 0 or -1. It's 2, 3, 4, some positive integer greater than 1. Okay? Now, when it comes to n being an odd integer value, then there's nothing more needs to be said, because a can be any real number, positive or negative, anything, and then b could be anything as well. And there's no issue with when you plug in a certain value with an odd index, when you plug in a certain a value, that maybe there's 2 potential b values, so you have to apply some extra restriction. So when it comes to n being odd, this is, we're done. This is all the description you need for the principal nth root of a. However, when we have to add a little bit more here to fully define this principal nth root of a number, we have to add a little bit more in regards to if n is even. And so all we need to say is that if n is even, then there's 2 statements we need to make. One is going to address that you can't put a negative number inside here or there's no solution. Until we invent imaginary numbers, there's no solution. So a has to be positive if n is even. Okay, so we've satisfied that one issue, but there's another issue. That so if a is positive, but then at the same time b needs to also be positive or greater than or equal to 0. A could be 0, then b is 0. But outside of 0, like b needs to be positive. And we have to say this as well, because we know that, like, if you have the 4th root of 16, well, there's 2 numbers. There's 2 real numbers that when you take them to the 4th power, you get positive 16. 2 and -2. So, but with this restriction here, we know that this is saying the single value we're going to get is going to be just the positive 2, where the b is positive. And so that is the the full definition of the radical. That is how we understand the radical symbol. Okay, but the radical also comes into play with the definition of rational exponents. So if you've got some number, some real number, to a rational exponent, so a ratio of integers. Again, we're still just talking about real numbers here. We don't know what an imaginary number is. Then this part of this is an nth root radical. So this is equal to a to the m power, all of that being the argument of an nth principal root, or you could equivalently write that like this. Okay, but note though, this is still a radical symbol. Anytime you see a radical symbol, that's principal root. So like this is, it's not like if you saw a rational exponent, then that's not dealing with a principal root. No, by definition, the n in the denominator here of this exponent is an nth principal root, the radical symbol. Okay, now up to this point, we've only opened the door just a little bit for having the radical interact with imaginary or complex numbers. Just a little bit, but not much. Okay, so all we have said was that we've expanded this radical definition to allow for negative numbers as the argument, not if n is even, but if n is for one case where n is even when n is 2. And that's it. That's as far as we've gone. So we've said that, okay, if you have a principal square root of a negative number, like -4, then you can simplify this by taking out an I and leaving the positive principal, well, the principal root of +4, which we know we can evaluate that as 2. So this is equal to 2i. Okay, but remember, this absolutely does not apply for something like this. You cannot take out an I here. All right, the 4th root of 16 is 2. Absolutely not. This property only applies for principal square roots. Okay, and you know this actually kind of makes a lot of sense because it works just like principal square roots of positive numbers in the sense that, so 2i squared is going to be -4, but then if you take the negative of this and you square it, that's also going to result in -4, right? -2 squared is +4, I squared is -1, -4. So it's like it's just like what we see with something like the square root of 16, +16. That's going to be +4, but we know the other root, the other square root, not principal root, but the other square root of 16 is -4. And so, you know, just analyzing the root of -4 as a complex number, -4 plus 0i, we know that the two square roots of -4 plus 0i are, they're going to be 2 plus 0i, right? But you choose the positive one, so that's great. That works out nicely, okay? But again, I want to stress, it's really important for you to understand that other than this, we have not gone any further regarding interactions of radicals, the radical symbol, with complex numbers, right? So as we were learning how to find roots of complex numbers in the trigonometry textbook, we weren't putting any complex numbers inside of radicals. We were just asking the general question or making the general statement, you know, list all of the roots of this number, all of the fifth roots of this number, just making the statement. In the same way you could say, you know, list all of the square roots of 64, or what are all the square roots of 64? Well, okay, that's what you're saying. What are all the numbers that when you square them, you get +64? Well, that's 8. One of those is 8, and one of those is -8. That is strictly how we approached finding roots of complex numbers. There were no radicals involved. Okay, and so with that, my recommendation for you going forward until you take a course in complex analysis, which there is going to be, at some point, there's going to be a playlist on this channel where we go through this complex analysis textbook. Okay, so until you've taken a course like this, my recommendation would be that outside of what is shown here about the pre-algebra definition of the radical, the principal root, as well as this property that we learned with imaginary numbers and the principal square root, there should be no more interaction of complex numbers and radicals than that until you get to the complex analysis course. It's just going to confuse you. Okay, now there is, though, one caveat where there is kind of an interaction between radicals and complex numbers. The caveat is this. So if we're asked to solve the equation x to the fifth minus 32 is equal to 0, okay? Solve this equation. Well, all right, this is a polynomial equation, so in general polynomial equations, you factor, you bring everything to one side, factor it, but we don't have to do that here because it's simple enough. We can add 32 to both sides. Okay. Now we can take the fifth root of both sides. X, the fifth root of x to the fifth is x. Okay. And now, but this is a little bit confusing because we do have, when solving equations like this, there is the square root property where if you had something like x squared is equal to 4 and you take the principal square root of both sides, you put a plus or minus like that. And you could even do that when solving an equation like this. Same idea. So you get x is equal to plus or minus 2, x is equal to plus or minus 4i. Those are both correct. Okay, but outside of principal square roots, that there's no rule for like, well, what are you supposed to do if you add or if you take a radical of both sides of an equation? Okay, well, now that we know how to find all of the roots of any number, so like 32 is a complex number, right? We could ask, what are all 5 of the fifth roots of 32 or 32 plus 0i? We can list all of those out. The way you need to interpret this is the exact same way you interpret if you took an inverse trig function of both sides of an equation. You introduced the inverse trig function. Well, what do you do in that case whenever you do that? Well, you don't treat the inverse trig function as far as like, what it's exactly asking you to output, the actual function itself. That's the same idea here. You wouldn't look at this as like, okay, the principal fifth root of 32, and that's it. No, you wouldn't do that. You look at it from the big picture perspective. Like with the inverse trig function, you look at it from the perspective of if you took the inverse sine of something to isolate a theta, some value, then you look at it from the pure big picture of, okay, what are all of the angles that when I take their sine, I get this number here. And you want to list out all those angles. That's how you look at this. It's really, you're asking, what are all of the numbers that exist that when I take them to the fifth power, I'm going to get 32. And we know, well, there's going to be 5 of those, and so you list all of those out. And so the difference in this case, where you kind of have a radical interacting, like in that case, you're treating this like it's a complex number, absolutely, right? But like you can see, but this is not really a principal fifth root, even though it is a radical. But it's more of, it's since you introduce it to the equation, we're not really looking at it that way anymore. We're really more of looking at it like, okay, list all of the 5 fifth roots of this number here. Okay, and you could even look at the square root property the same way, in the sense that you don't even have to, if you don't want to, you don't even have to apply the square root property anymore and put the plus or minus. That's just a shortcut. If you just left it like it is and you just answered the question, what are all of the numbers that when you square them, you get positive 64, you're going to get what the square root property would give you anyway. Okay, so that's the only exception to where you would kind of let complex numbers interact with radicals. That's the only exception. Other than that, my recommendation would be to have no interaction between radicals and complex numbers outside of this here. Other than this, just stick to the pre-algebra definition of what a radical is. Okay, but now, why am I saying that? Why am I recommending that you don't mix complex numbers and radicals past something like this? Okay, well, just to give you a preview of something we're going to learn in complex analysis, the answer to the question of, let's say we had the complex number 3 minus 2i. So does this have like principal roots? Like could we find the principal third root of this? The answer is yes. And how you find that root is actually really simple. So, you want to find the principal third root. You go through the same process that you would for finding all 3 of the cube roots of this. So convert it to polar, get the radius. And then when you get to the step of finding the 3 angles, okay, we know that there's going to be, so for a third root, there's going to be 3 separate k values. The principal nth root of a complex number is just the complex number with the angle corresponding to k being equal to 0. That's it. Really simple. That's a universal principle across the board. The principal nth root of any complex number is just of the n roots that there are. The principal one is the one that corresponds to k being equal, with the alpha that corresponds to k being equal to 0. Okay? So you might say, well, all right, that's great. So I can do this. What is the principal third root of 3 minus 2i and just go get that complex number and put it here? Well, no. We don't want to be mixing complex numbers with radicals like this. And, even in the previous video where we reviewed everything we learned about complex numbers in trigonometry, towards the end of that video, I threw in some complex numbers inside of radicals. I shouldn't have done that. That's way too confusing. I shouldn't have done that. Okay, but why not? Why not? What's wrong with this? Okay, well here's the issue. So let's find the principal cube root of minus 8. Well, based on the definition of the principal root radical here, we know this is equal to minus 2. Right? Okay, but now let's do it. Let's treat this like it's a complex number and find the principal third root. All right, so let's convert this to polar. That's going to be right, because it's on the negative horizontal. So the r values are going to be 2. So, okay, we're just looking at the x1 here. So it's going to have radius 2. Okay, now the alphas, we put 180 plus 360. Okay, and then k is going to be equal to 0, 1, and 2. So when k is equal to 0, we've got 180 divided by 3. So that's, okay, and then let's do the second one as well. We'll do all 3. When k is equal to 1, well, we know they're going to be spaced 120 degrees apart, so this is going to be 2 cis. Okay, well, we have a problem here. The minus 2 corresponds to k is equal to 1. According to complex analysis, which, I mean, that's like the reality, I would assume. I mean, we're looking at all, the full scope of numbers, right? The principal third root of minus 8 is this, which would be, I think it's 1 plus I root 3. I mean, so shouldn't this be 1 plus I root 3? Well, no, not necessarily. That's what's confusing. And that's what, in the previous video, I talked about that there's different contexts where you'll talk about all of the numbers that exist in math. One of the contexts is like you kind of treat all real numbers like they're in their own world, the real number line. They're in their own world. And the other context is when you you actually consider all numbers as, because we know real numbers are, in actuality, real numbers are complex numbers, just with a zero imaginary component, right? This is the real number line. But you're not even supposed to put this. That's why they don't want you putting that real number symbol here. You're supposed to put, right? That's the complex plane. So there's those two contexts, right? And we'll talk about this more when we go through the complex analysis course. But my recommendation would be that anytime you're dealing with a radical symbol, anytime you're dealing with a radical symbol, this, okay, then you're in this context for the most part. Again, there's exceptions with the minus, right? Well, then you're kind of in the imaginary complex world, but for the most part, you're in this world here. And in this world, in this world, so I'm referring to this here, what we learn in pre-algebra, in this world, this here means -2. In this world, the principal cube root of -8 is -2. Okay, but again, once you get into the complex analysis course, we'll open up this dialogue again and try and get a better sense of, what's the exact terminology when it comes to roots and principal roots and what radicals, etc.